Hello everyone. I hope you have remembered what we discussed in our previous lectures in the stochastic processes. So, we have discussed the basic probabilities and things what we need to incorporate with the calculations of stochastic processes, and also we discussed the first step analysis in stochastic processes. So if you can remember, we discussed the gambler's ring, right? So if I just memorize what we discussed in our previous lecture. So when it comes to the first step analysis in gambler's ring, the problem that we discussed was you are going to start with X amount of money and we are going to toss a coin. So if you receive a head, that is you will win the game and you will receive another $1. And then if you receive tail, right, that is you are going to lose the game, that is you will lose $1 from you. So eventually sometimes you may ended up zero in your hand, that is you will lose all your money, or else this game will stop if you receive n amount of money in your hands, right? So this is the concept of gambler's ruin. So in this case, since we are using a coin, a fair coin to toss, so that is you have 0.5 probability to receive $1. At the same time you have 0.5 probability to lose $1 from you. Okay, so in this case our problem was how to calculate the probability of losing everything in your hand, that is the probability of the gambler's ruin, that is you end up with $0 in your hand. So just to illustrate the problem, we were looking at this figure, that is you have X amount of money in your hand, and when you toss the coin, that is you can get into this first step with 0.5 probability, that is you will end up with X plus 1 amount of money. Or at the same time, if you lose this, that is if you receive a tail, again you have 0.5 probability to move into backward, right? So that is you'll end up with X minus 1 amount of money. So when you come to this state, that is if you are in X state X, you have two first steps, that is you can move to X plus 1 state or you can move to X minus 1 state. So our problem was to find the probability that where you end up with 0 starting with X amount of money, right? So that is the eventual ruin. We want to calculate the probability of ruining, right? So we take that event as R, okay, and then we know, so the current amount that you have in your hand, it is a random variable. You can start with 0 amount in your hand, you can start with $1, $2, right? So it depends. So it's a random variable. So the probability of ruining, when you have X amount of money, we take it as Px as per the notations. So if you can remember, we discussed how to solve this problem using second order differential equations, right? Because here you have two constraints. So I will quickly memorize what we discussed. When you take P0, that is you are starting with 0 amount. You have no money in your hand, but you are starting the game. In that case, if you calculate the probability of ruining, if you have no amount and no amount in your hand, so that is you're already ruined. So the probability is equal to 1. In the other hand, if you have capital N amount in your hand, if you calculate the probability of ruining, that is you have reached to the maximum point of your game. So that is, in that case you cannot ruin, that is you have already won the game. So the probability of ruining in that case is equal to 0. So when you take the first step analysis, as I showed you in the figure, when you have X amount in your hand, you have two first steps. That is, you can go to state X plus 1 if you receive a head, and you can go to state X minus 1 if you receive a tail. So since we are tossing a fair coin, you have the same probabilities, that is 0.5. So in this case, if you take here, we can consider the two first steps. That is, now in this case we can go to state X plus 1 with 0.5 probability, or we can go to state X minus 1 with 0.5 probability. Then again, when you are in state X plus 1, again you have two first steps. Again you can go to state X plus 1 minus 1, that is, you can go back to state X, or you can go back to state X plus 1 plus 1, that is state X plus 2, right? So in this case, if I write this using notations, this is Px equal to 0.5 times Px plus 1, since you are in state X plus 1, plus 0.5 into Px minus 1. With the boundary conditions, P0 is equal to 1 and Pn is equal to 0. So if you solve this with the boundary condition, so we know X goes from 1 to n minus 1, because X can be any amount. X can start from 0 to capital N, but since you have two constraints, two special conditions for X0 and X capital N, here when you take this equation, X can goes to 1, X can start from 1 to capital N minus 1. So this is in the format of a second order differential equation. So if you take the solution of a second order differential equation, I'm sure that you have discussed that when you were taking the maths courses in your second year, right? So in that case, we know the solution is in the format Px equal A plus Bx. So what we need to find is the two constants A and B. Since you have the two boundary conditions, what we did was we substitute 0 for the equation and found the A value is 1, and then we substitute capital N for the equation, and then we found the B value is minus 1 over N. Therefore we can write Px as 1 minus X over N by substituting the values, right? So in that case, this is the solution. If you have X amount in your hand, the probability of ruining the game is equal to 1 minus X over capital N, right? And if you want to find out the probability of the complement, that is, if you want to find out the probability of gamblers win, the complement of what we have found, so that is 1 minus the probability of ruining, that is what we have already found. So 1 minus, if you substitute 1 minus X over capital N, that you can simplify into X over capital N. So the probability of winning, probability of gamblers winning is equal to X over capital N. So I told you in this case, the same question we can solve using two other methods as well. But the easiest method is using this second order differential equations. But if you really want to use these two methods, you can use. So one is the solution by inspection. So in this case, since we are using a fair coin to toss, we have 0.5 probability, or in other words, you have the equal probability to receive at the same time to lose the same amount of money from your hands, right? That is, if you just graph this thing, what is happening here, so you have 0.5 probability of moving up or down from any step, right? So that is a special case. So if you just take here, if you look at this graph, I have taken the x values to x-axis, that is that is the amount that you have in your hand, so it can be equal to 0 and it goes up to capital N. And in this case my y-axis is the probability, so the probability of gambler's ruin. So we know when you have 0 amount in your hand, the gambler's ruin is equal to 1. And also when you have capital N amount in your hand, gambler's ruin is equal to 0. So between these two conditions you have several steps, right? But the important thing is now we have found px is equal to 0.5 into px plus 1 plus 0.5 into px minus 1. So if we rearrange the same thing, you can write it down as px minus 1 minus px is equal to px minus px plus 1. That is what's happening here is. Now in this case you can see, if you take the distance between px minus 1 and px, it is the same distance as the px minus px plus 1, right? So that is, if you take this point, right, if you take this distance and this distance, here you have the same distance between any two steps. This is a special case because we are using the same probability, since we are using the using a fair coin. So between these two steps you have a equal distance, right? So since you have n steps here, and since this is starting from 0 to capital N, since you have n distance, and since you have equal distances between these n steps, if you want to calculate the value or the distance of these two steps, that is equal to 1 over capital N, because the whole distance is capital N and you have n number of distances and all the distances are equal. So each step has a size of 1 over capital N. So in that case we know P0 is equal to 1, and in this case if you substitute the value of P1, right, P0 is equal to 1. So if you take P1 here, P1 is coming at this point, so this value is equal to 1, so P1 is coming here, that is 1 minus, you need to take this small distance, so this small distance is 1 over N, so P1 would be 1 minus 1 over N. And if you take P2, you have to subtract two distances from 1. So this distance is 1 over N, this distance is 1 over N, that is the whole distance is 2 over N. So P2 would be 1 minus 2 over N. So if you look at the pattern of this equations, you can see P1 is 1 minus 1 over N, P2 is 1 minus 2 over N. So likewise, if you recognize the pattern, we can write Px as 1 minus x over capital N, right? So by inspection, if you are going to find out the answer, you can use a graph like this and find out the probability as 1 minus x over capital N. It's same as what we found using the differential equations, right? And also there's another method, that is by repeated substitution to the equation also we can find out the answer. But I don't encourage you all to find the answer by repeated substitution because it takes long time, right? So it's much easier to find the answer using second order differential equations. Anyway, if you look at this, now this is the equation that we have derived so far, right? So here that is Px equal to 0.5 into Px plus 1 plus 0.5 into Px minus 1. So you can multiply the whole equation by 2, and then you will receive this, that is px plus 1 is equal to 2 times px minus 1. So since I have the two boundary conditions to x0 and x capital N, when x equal to capital N, what I'm going to do is I'm going to start substituting the values to these equations from x equal to 1. So when x equal to 1, here P2 is equal to 2 times P1 minus 1. And when x equal to 2, P3 is equal to 2 times P2 minus P1. But for P1, now you can substitute from this equation, right? So that is when you substitute from this equation, you will get P3 is equal to 3 times P1 minus 2. And when it comes to P4, you have 2 times P3 minus P2. But for P2 and P3, again, you can substitute from the equations. And we get 4 times P1 minus 3. So if you observe the pattern here, see, when it comes to P2, P2 is equal to 2 times P1 minus 1. P3 is 3 times P1 minus 2. And P4 is 4 times P1 minus 3. That is, if you write it in the general format for Px, that is x times P1 minus x minus 1. Right? And if you write it for Pn, that is n times P1 minus n minus 1. Right? But we know at the boundary values we have P capital N is equal to 0. So if you substitute 0 here, you will get n capital N P1 minus n minus 1 is equal to 0. That is P1 is equal to 1 minus 1 over capital N. So if you take the Px equation, now we can substitute the P1 value to this Px equation. That is, we have x times, for P1 you can substitute 1 minus 1 over n minus x minus 1 you have here. So when you simplify, you will end up with the same equation, that is Px is equal to 1 minus x over n. Right? So this is what we discussed, that is the first step analysis in our previous lectures. So today, that was a quick recap. So today we are going to talk about the expectation and the variance, right? Because in order to do the calculations, some things that you have already learned in your first year and second year, but to calculate some of the answers, we need a good understanding about the variance and the expectation values. So we are going to quickly go through the concepts of expectation and variance here, right? So in this case, so when it comes to the expectation, the mean value, right, or the expected value, we know when you take a random variable, we are always discussing about two types of random variables. You have continuous random variables and we have the discrete random variables. So we know when you have a continuous random variable, and if you have asked to calculate the expected value of a continuous random variable, and if you know the probability density function, what you have to do is, in order to calculate the expectation, you take the probability density function and you take the random variable, so x into the probability density function, you have to integrate that within the whole range of x. Right? And in the other hand, if you take a discrete random variable, in order to calculate the expectation, what you have to do is you take all the possible values of x, multiply that with the probability of that x, Or in other words, if you take the probability mass function, when you substitute the x value, that gives you the probability, right? So you take x, multiply that with the probability, and you have to take the summation of all x values, right? So this is how you find the expectation to a continuous and a discrete random variable. I'm sure since y'all are statistics special students, you are very familiar with this. And also when it comes to a function of x, that is when you have a random variable x and when you are given with a function of x, again you can calculate the expectations. That is, if gx is a function of x where x is a random variable, then if x is continuous, what you have to do is you have to integrate to calculate the expectation. That is, you take the function gx, you take the probability density function, and you have to integrate that within the full range of x. And on the other hand, if x is discrete, you have to substitute x value for the function gx and then find the probability at the point x, multiply, and you have to take the summation for all the values of x, right? So why we are concerned about the expectation of xy? So when it comes to xy, let's say you have two random variables, capital X and Y. So sometimes these two random variables can be independent. That is, the value of x has no effect on the value of y. Oh, in the other hand, sometimes x and y can be dependent, right? That is, when we observe a value for your random variable x, it might influence the random variable y also, right? For an example, if you take x as the height of a randomly selected person, and if you take y as the weight, right? So there is association between x and y. Okay, so in this case, what we do is to understand the meaning of the expectation of xy, right? So what you have to do is we have to collect a large number of pairs from x and y, right? And then in this case, if x and y are dependent, so if you take any value of x, it might affect the value of y, right? So in this case, when you collect large number of pairs, in order to calculate the average of these pairs, we use this expectation of xy, right? So that is why we are interested in xy. And also in statistics, we know we are calculating the covariance and we are calculating the correlation of the random variables which are closely related. So in order to calculate this covariance and correlation also, this expectation of xy is also important. Right? So if you talk about the properties of this expectation, we know if you take, let's say, g and h are two functions of the random variable x. So it can be discrete, or x can be discrete, or x can be continuous. In that case, if you take the expectation of a into gx plus b into hx, so this is a function of x. So this, when you have constants and when you are calculating the expectation, we know you can take the constants out. So that is a times e, the expectation of function gx, plus b times the expectation of function hx. So we know how to find the expected value of function, right? So in generally, when you have a constant, let's say we are going to calculate the expectation of a times x plus d. So that is simply equal to a times expected value of x plus b. Right? So if you have any two random variables, that is That can be discrete, continuous, independent or non-independent, but when you write the expected value of x plus y, that you can write as expected value of x plus expected value of y. Right? So in generally, even if you have n number of random variables and if you are concerned about the expectation of the summation, that you can replace by the summation of the expectations. So when you have two independent random variables, and in that case if you are going to talk about the expected value of the multiplication, that you can write, that is the expected value of xy, this is equal to expected value of x into expected value of y. At the same time, if you have two functions of x and y, where x and y are independent, again you can write it as expected value of, if you are going to find the expected value of gx and expected value of hy, you can replace that by expected value of gx into expected value of hy. Right? So, but what you have to remember is you can use this when x and y are independent, right? Only the expected value of ex is equal to expected value of x into expected value of y, only if x and y are independent, right? So, that is, if x and y are independent, then this condition is true. But when the converse is not true, that is, if expected value of x into expected value of y is equal to expected value of x and y, you cannot say they are independent. But it's possible to use the same equation when they are dependent as well. Okay, so because of that, the converse is not true. When they are independent and dependent, you can use the same equation, but the converse you can't talk about when x and y are dependent. Okay, so we'll quickly have a look on this the example. So if you take A to be any event, right, we can write PA, right, as an expectation. Okay, right, we'll look at this example. Then if you take this indicator function, that is, I have taken A as an event. So let's take this indicator function IA, that is IA is equal to 1 if event A occurs, and IA is equal to 0 if it does not occur. Right? So that is, in this case, I'm going to calculate the, you can see this indicator function is a random variable. It has two values, 1 and 0. 1 is when A occurs, otherwise it's equal to 0. So IA, the indicator function, is a random variable. So if you take the expected value of IA, that I can write as, since this indicator function has two values from 0 to 1, so I'll take the values of the indicator function as r times the probability of r with its full range. I have to take the summation of that since it's a discrete random variable. So when r is equal to 0, I have to calculate the probability, that is the indicator function is equal to 0, plus when indicator function is equal to 1 into the probability when indicator function is equal to 1. So since this part is 0, that you can omit, so you are left with probability where the indicator function is equal to 1. So we know when indicator function is equal to 1, that is where the event A has happened, right? So that, in other words, we are calculating the probability of event A. So I can write it as probability of A. So I can write the expected value of IA, the expected value of this indicator variable, is equal to is equal to the probability of event A. So this is true for any event. So when you are doing the calculations, you can use this result with any event. And then we can talk about the variance, covariance and correlation as well. So if you take the random variable x, right, we know the variance is, it always tells us about the spread of your random variable, right? We know if the values of the random variable are clustered tightly around the mean, we can observe a small value for the variance. So in the other way, if you have a big spread, if the values of the random variable x has been distributed in a big range, you can observe a higher value to the variance, right? So in this case, let's take capital X be a random variable. So we know you have used this equations, right? Equation before also, I'm sure. The variance of any random variable X is equal to X minus the mean value of that random variable, and you have to square it and take the expectation. So we know when you are taking the variance of a random variable, in other words, what we are doing is we are taking the expectation of the difference between the random variable, the squared difference between the random variable and its mean, right? So you have to take the random variable, subtract the mean value, square it and take the expectation. So we know the same equation is equal to expected value of x squared minus expected value of x, the whole thing squared. Right? So this result, I'm sure that you have used it in your first year and second year, but if you have forgotten it, right, so we'll quickly look at this example so you will remember how to use this result when you are calculating the variance value. Right? So let's say you have a continuous random variable capital X, and I have given you the probability density function here, right? So you can see the probability density function of random variable X is equal to 2 into x to power minus 2 when x is in between 1 and 2, otherwise it's equal to 0. So if we are supposed to calculate the variance, we know first we have to calculate the expectation, since we have expectation here to substitute. So we'll start with expected value. So you have to take the function, multiply that with the random variable and integrate in its full range. So I'll take x as my random variable. Function is 2 into x to power minus 2. Since x is only in between 1 and 2, I have to integrate it from 1 to 2. So when you simplify the function, you have 2 into x to power minus 1, that is, this is 2 into 1 over x, right? So we know you can, when you integrate 1 over x, you can write it as log x, right? And then you can substitute the range, that is 2 into log 2 minus 2 into log 1, right? So that is, you can write as 2, when you simplify, you can write it as 2 into log 2. Okay. Because here what I have done is, you can take 2 out and you can write this subtraction as log 2 over 1. So that is, again you have 2 into log 2. Okay. So the expectation of the random variable x is 2 into log 2. And since the variance is equal to this equation, now you can substitute to expectation, but again we have to find the expectation of x squared. So I'll take the function and I'll take x squared. So x squared into function is 2 into x to power minus 2, and I have to integrate that in the full range, that is x goes from 1 to 2. So when you simplify this, you can see x squared will omit and you are ended up with only 2. So when you integrate that, you have x here. So when you substitute the values, the expected value of x squared is equal to 2. Now we can find the variance, that is when you take the equation expected value of x squared, we have found it as 2 minus expected value of x is 2 times log 2. So you have to take the squared value of that, and then when you simplify, we can find the value as 0.0782. Right? So at the same time, we can calculate the covariance as well. So the variance always gives you the, it talk about the spread of your random variable. And when it comes to the covariance, it's always a measure about the association or the dependence of two random variables, x and y. Right? So this I think you have you can remember, because we all know when you take the variance, since we are talking about the expectation of a squared value, it's always a positive number, it cannot be negative. But when it comes to covariance, since it's talking about the association between two random variables, it can be positive or negative. Right? For the covariance, positive and negative figures both are possible. So when it comes to two random variables x and y, and if you are interested about the covariance, we can find the covariance using this equation. Right? That is, the covariance between x and y is equal to, you have to take the expected value of this term, that is, you have to take the random variable x, subtract its mean, into random variable y, subtract its mean. That is the difference between the random variable x with its mean into difference between the random variable y with its mean, and then you have to take the expectation of this multiplication. So we can show, when you simplify this, it's equal to expected value of xy minus expected value of x into expected value of y. Right? So in this case, you can use any equation which is familiar with you. Right? So I told you the covariance is it can be positive and negative both. So you can observe a positive value for the covariance when you calculate the covariance between two random variables if the large values of the random variable x is having association with large values of random variable y, or the small values of random variable x is having association with small values of random variable y. Right? So if that is your case, we can observe a positive figure for the covariance. Right? So in the other hand, if you take small values of random variable x, if you can see association with the large values of random variable y, in that case you have a negative association. Right? So that is, your covariance is a negative figure. Now for an example, if you take x and y as height and weight, right, normally we believe that if your height is if you have a high value for height, you will get a high value for weight as well. So the large values are having an association with large values. In that case, the covariance is positive. But if you take the heart rate and if you take the age of a person, in that case, if you calculate the covariance, it will be a negative value. Okay, so you will observe this when you are doing questions, but you can keep this in your mind, because when you do a calculation, right? You can check whether your answer is correct or wrong when you have these small things in your mind. So if you take any two independent random variables x and y, right, and if there is no pattern between large values or smaller values, so that you can write the covariance between x and y is equal to 0, right? This is a very important result. So what you have to remember is, if x and y are independent, then the covariance of x and y are equal to 0. But if the covariance of x and y are equal to 0, you cannot say they are independent, right? Because there is another constraint, they should be normally distributed as well. Okay, but if they are independent, you can directly use the result where the covariance of x and y is equal to 0. Okay, and if you just talk about the properties of this variance, so if you take a and b as any two constants, and if you take capital X as any discrete or continuous random variable, so we know when you calculate the variance of a constant, it's equal to 0. So if you want to calculate a gx plus b, the variance of this term, when you take the constant out, you have to take the squared value of that. So that is a squared into variance gx, right? So, and if x and y are independent, when you are calculating the variance between x plus y, that is equal to variance of x plus variance of y. But if x and y are not independent, variance of x plus y you have to write as variance of x plus variance of y, plus then you have to consider about the covariance as well. That is 2 times covariance of x and y. Right? So you have to remember well. So this part is, the covariance part is not coming when x and y are independent, since it is equal to 0. Okay, and then again, if you are interested in the linear relationship between any two variables, then you can calculate the correlation. So I'm sure when you learn about the regression analysis, you have to calculate the correlation. In that case, we know we are always concerned about the linear relationship. So we know the correlation coefficient gives us the value minus, it can be any value in between -1 and +1, right? So if you want to calculate the correlation of any two random variables, that is equal to the covariance of xy divided by the square root value of variance of x into variance of y. But the correlation part, it's not actually, we don't talk about that much in the stochastic processes. But since we discuss about the correlation, when you have the correlation, covariance, you can calculate the correlation value as well. Okay. So actually, when it comes to the stochastic processes, what we are interested about is the conditional expectation and the conditional variance of the random variables, right? So that is something very, very important when it comes to stochastic processes. So let's say, now here, in order to illustrate how to calculate the conditional expectation and the conditional variance, I'm going to stick to a discrete random variables, but it will be the same process for the continuous random variables as well. So if you can understand the discrete random variable part, you can apply the same concept to the continuous random variables as well, right? So now let's see, I'm going to take this x and y as two discrete random variables, and they are dependent, right? That is, there is an association between x and y. Now let's say, so x will have so many values, and y will have different values as well. Let's say first I'm going to take the random variable y, and I'm going to fix this random variable y at the value simple y. That is, for an example, let's say y can take 10, 20, 30 and 40. So I'm going to fix y where y is equal to 20. So you can take any value, right? So I'm going to take the random variable y and I'm going to fix it at the value simple y. And then what I'm going to do is, now the value of y is fixed. So I can observe what will happen to my x random variables or x values when the value of the y is fixed, right? So that is, I'm going to calculate the probability of each value of random variable x when y is fixed. So that you can write the probability where our random variable x is equal to simple x, right? Given that the random variable capital Y is equal to simple y, we have fixed that. So that is our condition. So since we are going to calculate the probability based on this condition, okay, this is the conditional distribution of x, right? So you can write this as the conditional distribution of x given that random variable y is equal to simple y. Okay, so in this case, since we are talking about these two discrete random variables, so when you are calculating the conditional probability function, we can write it as the probability of random variable x is equal to simple x given that random variable y is equal to simple y. This is equal to probability when capital X is equal to simple x and capital Y is equal to simple y divided by probability capital Y is equal to 1, right? So these are coming from the conditional probability part we discussed, the same as that, right? You can apply the same concept. So actually what we then when you calculate the conditional probabilities using this function, so we can find we can write the conditional probability function like this. That is, if you are concerning about the conditional probability function of x given that y is a specific value, you can write it as f x given y, right? And then that function value you can calculate probability where x is equal to simple x given y is equal to simple y. So we know when you calculate a probability mass function, when you take the total of all the probabilities, it should add up to 1. So same here. Since we have calculated the conditional probability function, when you take the total of the conditional probabilities, that should add up to 1. Okay, so that should add up to 1. So you take the conditional probability function and you take the summation of all the possible x values, and that should add up to 1. Okay, so when you have two random variables, now since we have calculated the conditional distribution function, right? So this is the conditional distribution, conditional probabilities, and now we know what is the conditional probability or the conditional distribution function. Since we know the conditional distribution function, now we can calculate the conditional expectations as well. Okay, so in this case, we can calculate the conditional expectations. That is, when you take the expected value of random variable x, given that random variable y is equal to simple y. So I can write it as a conditional expectation. That is, we are going to find the expected value of x given that your random variable y is equal to simple y. Right? That is expected value of x given expected value of y is equal to simple y. So this is equal to, since this is the discrete case, you have to take all the values of random variable x, multiply that with the probability. You can find the probability using the conditional distribution function, and then you have to take the summation over the range of x. Right? So when it comes to the continuous case, same concept, but you have to use the integration. Right? And so that is when you take the conditional expectation, that is the expected value of x given for a specific value y, right? That means we are going to find the mean value of our random variable x when y is fixed at a point, fixed at y. Okay, so in this case, when you take the unconditional expectation, right? Let's say the expectation of x, when there is no condition, the unconditional expectation, we just write it as expected value of x. So it can be any number, right? When you calculate the unconditional expectation, it can be 2, it can be 5.8. So it can be any number. It can be a it can contain decimal points as well. But when you calculate the conditional expectation, it's also a number, but that number is always depending on y. Right? For an example, when you calculate the expected value of x given y is equal to 2, so you get a number when y is equal to 2. Right? Or if you calculate the expected value of x when y is equal to 3, you will receive a expectation, a value, a number when y is equal to 3. Right? So actually when you calculate this expected the conditional expectations, it's actually a function of y, because since we have fixed y, when y is changing, your expectation is also changing. So actually you can observe it as a function of y. Okay, so in this case, if you want to find out here, since we can observe this conditional expectation as a function of y, so what you have to do is, when we are calculating this, when we evaluate the conditional expectation, first we have to choose a fixed value for y, and then the expectation of x we have to find when the expectation when the value of y is fixed. Right? So that's how we evaluate the conditional expectation. So we'll look at this example, then it will be much clear for you. Now let's say in this case, let's say you have the random variable y. It has two possible values. So I'm going to take the discrete random variables as I told you in the beginning. So random variable y has two possible values, that is y is equal to 1 and y is equal to 2. And then when it comes to x given y, that is the conditional distribution, we can see it's equal to 2y and 3y with the probabilities 3 over 4 and 1 over 4. That is, now we are going to calculate the conditional expectation of x given y. So you have to calculate the values of x when you fix the value for y. For an example, now you can see y can take only two values. It can be either 1 or 2. Now let's see what will happen to x when y is equal to 1. So when y is equal to 1, we have to find out the values for x when y is given that y is equal to 1. So if I take the conditional function, so I have to substitute 1 here. That is 2 into 1 is 2, 3 into 1 is 3, and the probabilities are given. Okay, so in this case, based on this conditional function, distribution function, I can calculate the conditional expectation of x when y is equal to 1, right? That is the expected value of x given y is equal to 1. So that is the first possible value is 2 into its probability is 3 over 4 plus. The next possible value is 3 into its probability is 1 over 4. So when you simplify that, you will get the answer as 9 over 4. Let's see what will happen when y is equal to 2. So when you take the conditional distribution function and when you substitute 2 here, that is 2 into 2, 4. Probability is same, 3 over 4. And 3 into 2 is 6. Probability is same, 1 over 4. So in this case, if you calculate the expected value of x when y is equal to 2, that is 4 into the expected value 3 over 4 plus 6 into the expected value 1 over 4. Right? So that will give you the expected value of x when y is equal to 2. When you simplify that, you will get it as 18 over 4. So you can see for these two conditional expectations, we have received two values, two different values, because the conditional expectation is depending on your y random variable. So in the first case, we have fixed y into 1. In the second case, we have fixed y into 2. So it's depending on y. Right? So actually, see, here you can see the conditional expectation is changing. It's changing due to y. So we can say the conditional expectation is also a random variable, and the randomness is inherited from y, not because of x. Not from x. We can observe the expected conditional expectation as a random variable because of y. Because when y is changing, it's changing. So we can write the conditional expectation of x given y into a particular value y is equal to 9 over 4 when y is equal to 1. It's equal to 18 over 4 when y is equal to 2. Right? So it's always depending on the value of your random variable y. So remember well, the conditional expectation is a random variable and the randomness is inherited from y, not from x. Right? Since we discuss about the conditional expectation, the conditional variance is also very important in the stochastic processes. So when it comes to the conditional variance, it's actually similar to the conditional expectation. So let's say we are going to take the same two random variables x and y. So we are supposed to calculate the variance of x given y. Right, the variance of random variable x given y is equal to simple y. So that is, we are using these notations throughout, right? So that is the variance of x when y is fixed at the value simple y. Right? So in this case also, if you can observe the conditional variance or variance x given y as a random variable, right? Because it's changing due to y. And then here, when you take x and y as two random variables, the conditional variance of x and y, we can write it like this. That is, we know when it comes to the variance of unconditional variance, what we do is variance of x is equal to expected value of x squared minus we have to take the squared value of the expected value of x. Same thing we have done here. So you take the expected value of x squared with the condition, that is given the value y, minus you have to take the squared value of expectation x given the value y, right? So this is same as expected value of x minus mean value of x given y, whole thing squared, but you have to be concerned about this condition, that is the value of y. So we are always calculating all these values by substituting the y value for the random variable y. So just as the conditional expectation, the conditional variance is also random because it's changing the values, and the randomness is here also the randomness is inherited from the random variable y, because when we are changing y, it's changing not because of the random variable x. Right? So when it comes to the loss of total expectation and the variance, right? In this case, if you if all the expectations are finite and any random variable, if you take x and y as any two random variables, then we can write the expected value of x is equal to expected value of y into expected value of x given y, right? And then if you have a function of x, right, then you can write the expected value of the function of x as expected value of y into expected value of the function x given y for any function g. And the variance of x, you can write the expected value of y into variance of x given y plus variance of y into expected value of x given y, right? So this is the law of total variance, and the expected EY and the variance y are the expectation over y and the variance over y. We can say when we are given with the functions of y, function of y, we can easily calculate the expectation or the variance over the distribution of the random variable y. And so when you take the law of total expectation, so that says the total average is the average of case by case averages, right? That is, if you look at the function of the total expectation, when you take the expected value of x, what you have to do is first you have to fix the y value for a specific value, and then you calculate the expectation of that particular case, and then the expected value of the whole, then you have to multiply that with the expectation of all the y values, right? That is, we concern about case by case when you are taking the total expectation, right? So because we know when you take the expected value for x given y, it's different when you fix y value for different numbers, right? So what you have to remember is the total average is the average of case by case averages. So we'll do this example and see. Now in this case, in the previous, I'm going to use the same example, right? This one. So we have two random variables where we are given with the two probability mass functions for y and x. Now in the previous case, we saw the conditional expectations, right? We calculated the expected values when y is equal to 1 and y is equal to 2. right? So I'm going to use the same thing here. So we found that the expected value of x given y is equal to these two values with these probabilities. So if I'm going to find out the total average values, right? So I can find out the expected value of x. So one possible value for expected value of x given y is 9 over 4 with probability 1 over 8, plus the other possible value is 8 over 4 with probability 7 over 8. So this will give us the expectation of random variable x, right? So I have in this case, I have illustrated the proof for these three special cases. So I'm going to leave it as a homework for you. So you can just have a look and see how you can derive these equations, right? So all the steps are here. So you can leisurely have a look and see how to derive these equations. So let's see how to use what we have discussed so far, that is the conditional expectations and the conditional variance, right? Using this example. So it says one person is running a dolphin watch business. So what happens here is, if it's a rainy day, he cannot go for his work, right? So he has to stop working if it's a rainy day. Okay, otherwise he will be working for any given day, right? So you are given with some probabilities. So if you there is a probability of p to get a rain, or the probability of if you select any day at random, the probability of being it a bad weather day is equal to p, right? So when it comes to all the days are independent, right? So here they have defined two random variables x and y. So y is the number of consecutive days Fraser has to work between bad weather days, and capital X is the total number of customers who go on Fraser's trip in this period of y. Okay, so you have to calculate the conditional expectation on y for the distribution of x, right? So first you have to understand what is happening here, right? There is a person who's running a dolphin watch business. So if it is a bad weather day, he cannot go for his work. So that is, there is a probability to be it a bad weather day. The probability is equal to p. So if you count the number of consecutive days that this person has to work between bad weather days, that is a random variable. For an example, let's say this person is going to work today and tomorrow. So the next day would be a bad weather day. So he has worked 2 days consecutively. In that case, y is equal to 2. And let's say again he will work 3 days continuously, and then the following day would be a bad weather day. So then, since he has worked 3 days continuously, y is equal to 3, right? So y is the number of consecutive days that he worked between bad weather days, right? So y, you can see y is changing. Y is a random variable. It can be any number, we never know. We are just counting the consecutive days that Fraser has worked between bad weather days. Okay, and if you count the number of customers who go on trips in this period, then you can take it as x, right? That is, if you if this person has worked the first 2 days to get continuously, and in day 1 and day 2, let's say there are 20 customers. If you take the total as 20 customers, then x would be equal to 20 when the number of consecutive days is equal to 2. So given that y is equal to 2, x is equal to 20. Now let's say when you take the next 3 days that this person has worked, there are 15 customers. So x would be equal to 15 when y is equal to 3. Likewise, you have to take the total number of customers who go on trips in this period y as the random variable x. So you can see x is also changing, y is also changing. So both are random variables. So the first thing is we have to define the distributions of x and y. So when it comes to x, that is, we are counting the number of days, right, before we come across with the bad weather day, right? Whether this person has worked 2 days or 3 days, likewise. So that is, if you take a bad weather day, right? If you take a bad weather day, we are counting the number of incidents, or we are counting the number of days that this person has worked before this bad weather day occurs, right? So in other case, we can identify this process is having a geometric distribution, because if you take a bad weather day as a success, right, we are counting the number of failures until we get a success, right? So we can identify y is, if you take y as the failures here, that is the consecutive number of days that Fraser has worked, we are counting those failures, the consecutive number of days. So we can identify y is having a geometric distribution, and they are given with they have given us the probability of a bad weather day, that is the probability of is simple p. So we can easily identify y is having a geometric distribution with the probability p. So if it's a geometric distribution, we have discussed in our previous lectures that the expectation and the variance of geometric distribution is 1 minus p over p is the expectation, variance is 1 minus p over p square. Right? So all the general functions, the expectation and the variances of the general functions that we discussed in our previous lectures, you have to keep them in mind, because you have to use them in your calculations. Right? Now what you have to do is, if you consider x given y, it's having a Poisson distribution. Right? Let's see why it's having a Poisson distribution. When you take the distribution of x given y, x is the number of customers who are coming, who has gone on this trip in this period of y, right? So let's say, since we are counting the number of customers, right, within a given period, we can identify that as a Poisson distribution. So in that case, since there is a condition on y, right, now if you take the first 2 days that you have, if the period is equal to first 2 days, right, in that case, if you are concerning about the number of customers who have gone on this trip between the first 2 days, if the rate is equal to mu, that is per day, let's say there are on average mu customers, and if you are concerning about 2 days, so the average would be mu into 2, right? And if you are concerning about 3 customers, if the average per day, average number of customers per day is equal to mu, then if you are concerning about 3 days of period, that is the rate you can rewrite as mu into 3. So you can see when the y value is changing, the rate or the rate of the customers who have gone on this trip is also changing, right? So that we can see as mu into the number of days. So the number of days have been defined using y. So that is the, if you take the distribution of the number of customers x, given y, that is having a Poisson distribution, and the rate you can write as mu y. Okay, so if that is the case, we know when it comes to Poisson distribution, the expectation and the variance both are equal. So we can write for this random variable, the expected value of x given y and the variance of x given y both are equal to the rate, that is in other words mu y. Okay, so now we are going to calculate the expected value of x with the condition on y. So you can use the formula, you can take this formula from the law of total expectation that we discussed, right? That we know expected value of x is equal to expected value of y into expected value of x given y. So now we have found expected value of x given y. We can replace by mu y into expected value of y, right? So I'm going to take mu out since it's a constant, and then you can see expected value of x is equal to mu times expected value of y over the range of y. So that is basically we have to find the expected value of y. But here we have defined y is having a geometric distribution where the expected value is 1 minus p over p. Right? So we can substitute that here. So that expected value of x is mu into 1 minus p over p. Right? So for this particular example, we can find the expected value of x, or in other words, the expectation of the number of customers who have gone on this trip is equal to mu times 1 minus p over p. And when it comes to variance, we can use the total law of total variance. So that is this equation you can use. And in that case, we know the variance of x given y, we have already found that is equal to mu y here. So I'm going to replace it as mu y. And expected value of x given y is also equal to mu y. So here I'm going to take mu out, that is expected value of y over the range of y, plus, if I take mu out here, we have to square it since we are interested on a variance. So that is mu squared into variance of y over the range y. So expected value of y and the variance of y we know according to the geometric distribution of y, these two values. So I'm going to substitute it here. And then when you simplify, you'll end up with this result. That is the variance of x is equal to mu into 1 minus p into p plus mu over p squared. Right? So that's how we calculate this. And I have mentioned the R codes as well, but that part we are not going to discuss here. Is because as we need a laboratory, we'll discuss our practical part later on. And but if you have, you can download our and if you really want, you can just type all these codes and see, right? How to get the outputs as well. All right, so the next thing that we are going to discuss is the randomly stopped sum. So this is also very important concept in stochastic processors, the randomly stopped sum. So in this case, what we do is now when it comes to a randomly stopped sum, we are concerned about n number of events, right? Where the n events are random. It can be any number of events, but the important thing is each and every event is associated with a penalty or a cost or a reward. So what we are going to do is, if you have n number of events and if each event is associated with a cost or a penalty or a reward, we are going to find out this total cost or the reward, right? That's what we do in this randomly stopped sum. The difficult part is here the when you take the number of events, that is also random, and when you take each event, the cost, right, or the penalty or the reward, that is also a random value. So you have two random variables within one concept, right? So we call that as the randomly stopped sum. So in the stochastic processors, let's say you have capital N number of events, and if I take the first event as 1 and the associated reward or the penalty as capital X1, and then you can take the totals as X1, X2 up to Xn, right? So that is, we can denote that as Tn. So in stochastic processors, this randomly stopped sum is denoted as Tn. Okay, so the best example for this randomly stopped sum is the ATM machine. So we know if you take any given day for the ATM machine, we never know the number of customers who are going to withdraw money from the ATM machine, right? And also we know if you take the customers, they are withdrawing different amounts, right? So both are random variables, the number of customers and the amount that they withdraw, right? So now you have the new machines where you can deposit as well, but for this particular case, let's concern about the machines where you can only withdraw money. Okay, right. So let's illustrate our problem for the randomly stopped sum using the ATM machine example. Now let's say in a particular city, customers are withdrawing money, right? And if you take X as the number of money they withdraw, so we are giving with the probability function of X, right? So that is, here the customers have withdrawn 50, 100 and 200, and the probability of withdrawing 50 is equal to 0.3, 100 is 0.5 and 200 is 0.2. So we know if you concern about the number of customers who have used the ATM machine per day, so that is, we are counting the number of incidents which has happened, which have happened within a given period. So it's a Poisson distribution, right? So let's say the number of customers is equal to capital N, and it's having a Poisson distribution with rate lambda, right? So what you have to do is, we need to find the randomly stopped sum, that is capital Tm, where it's equal to x1 plus x2 plus up to xn, that is the total amount of money withdrawn in a day, right? So where if you take xi has the probability function which is given here, right? And these xi's are independent. Okay, So the first thing is we have to find the Tn, the randomly stopped sum, stopped by random number capital N, and then we have to show the expected value of x is equal to 105 and the variance of x is equal to 2725. So these two we have to show. So let's see how to do the calculations in that case. Right, so you can see I have given you the first part, that is part A, as an exercise, right? That is to find out these two values for the variance and for the expected values. But let's quickly see how to calculate this variance and expected value. Okay, and first I'll show you how to calculate the expected value. So the expected value of x, now if you look at the values of x, we are given with three values. So x is a discrete random variable. So if you are going to calculate the expectation, you have to take the value, multiply that with its probability, that is 50 by 0.3, 100 by 0.5, 200 by 0.2, and then you have to take the summation of all the terms. So I'm going to do that. That is, you have to multiply 50 by 0.3 plus 100 by 0.5 plus 200 by 0.2. So if you simplify, you will see this is equal to 105. So that is the first thing you are asked to show. The expected value of x is equal to 105. Then you have to find the variance of x. You have to show that is equal to 2725. Right? So we know if you want to find the variance of x, first we need to find the expected value of x squared. Right? So I'm going to find the expected value of x squared. That is, the first possible value of x is 50. So I'm going to take the 50 squared, multiply with its probability, that is 0.3, plus next possible x value is 100. So 100, I'm going to take the 100 squared, multiply with its probability 0.5. And then the next possible x value is 200. So I'm going to take 200 squared. Its probability is 0.2. So if you simplify this, you will get 13,750. Right? But this is not what we are interested. We want to calculate the variance of x. So variance of x, we know that is equal to expected value of x squared minus, you have to take the squared value of expected value of x. Right? This is what you have to concern. Now here, the expected value of x squared we have calculated, that is 13,750 minus expected value of x is 105. So I have to take 105 squared. And if you simplify this, you will see it's equal to 2,725. Right? See, the expected value of x is 105 and the variance is 2,725. So you can easily find out these two values when you are given with the probability mass function of the random variable. But here the important thing is, now we are going to find the expected value of the randomly stopped sum and the variance of the randomly stopped sum, which is new for the stochastic processors. Right? So what I'm going to do is, we know when you take the randomly stopped sum, capital Tn, that is equal to the summation of all the xi's, right? So that is summation of xi where I goes from 1 to n. And then, so when you take this the expected value of Tn and the variance of Tn, that is the mean and the variance of the sum of the independent random variables, right? So but there is a condition where this number of random variables is equal to capital N. So what are we going to do is we are going to find the expected value of Tn given that capital N number of random variables are there. So Tn we can replace by x1 up to xn given that capital N is the number of random variables. And now we can, since all the xi values are independent, right, and we are supposed to find the expectation of a summation, since they are independent, we can replace that by the summation of the expectations, right? So that is expected value of x1, x2, likewise up to xn. And then we know since we have n number of values, n is constant, right? So we can, since all the xi's are coming from the same distribution, right? They are having the same expected value or the same mean, and then I can replace this term by n into expected value of x. Right, that is because all are independent and all are having the same mean value. So that is n into expected value of x. So expected value of x we found, that is 105. So this is equal to 105 times n. So if you know the number of customers that has visited this ATM machine, in order to find out the expected value, you can multiply that by capital N. Okay, so that gives you on average how much you have to load to your ATM machine for withdrawal. Okay, so if you look at this now, if you want to calculate the variance of the randomly stopped sum, in that case you can calculate it as variance of Tn you can replace by x1 up to xn given that capital N is a constant, and then you have again independent random variables where capital N is a constant, right? And then here what you have to do is, since these are independent, we do not have to talk about a covariance, right? You can replace the variance of the summation by the summation of the variances, that is variance of x1, variance of x2, likewise up to variance of xn. And since all are coming from the same distribution, I can write the variance of the random variable as variance of x, and since I have n terms, can multiply this by n. So that is the variance of randomly stopped sum you can write as 2725 times n. Okay, given the random variable n. And in this case, what we are going to do is, if you don't have this condition, right, if you are going to just find the expectation of the random variable Tn, now we know by the formula that is equal to expectation of n into expected value of Tn given n, right? So that is expected value of Tn given n we found, that is 105 into n. So if you are going to find the expected value of this over the range n, you can take 105 out. So that is the expected value of n over the range n. So we know n is the number of customers who are visiting the ATM machine. So that is having a Poisson distribution. If you take lambda, the expected value, you can replace it by lambda. Similarly, you can find the variance of the randomly stopped sum as well, right? So the variance of randomly stopped sum, you can use this equation that we discussed. So you have En here, the variance of Tn given n we found, that is 2725 times n plus variance of n, this part we found, that is the expectation of Tn given n, 105 into n. So you can take the constant out here, and the expected value of n over the range n is lambda plus. If you take 105 out, you have to take the squared value, since it's a variance, that is 105 squared, that is 11,025, and the variance of n over the range n is equal to lambda. So when you take the summation, that is 13,750 times lambda, where n is having a Poisson distribution with the rate lambda, right? So here the R codes are also there. If you are interested, you can use the R codes and check for the same result in R. And therefore what we have to concern here is, when we are doing the calculations with the randomly stopped sum, right, that is expected value of the randomly stopped sum Tn, we can simply write as mu, that is the expected value of this random variable x, into expected value of n. Right? Likewise, when we want to find the variance of randomly stopped sum, that is equal to variance of this x values into expected value of n plus the expected we have to take the squared expectation of x into variance of n. So this result, this is the general result for randomly stopped sum. Right? So I think we are going to stop from this point for today. So if you have any question, you can directly email me, or else you can send me a message through Cal, right? So when we have the question forum also, you can come up with your questions, right? So I hope things we discuss up to randomly stopped sum is clear, right? So you have to go through with all these lectures, and if you have any questions, please let me know. Thank you.